Hello. So I've made a couple of mistakes right off the bat. I'm actually presenting using a new piece of technology to me that I've never done before. I'm just presenting off of a website. So wish me the best of luck using a Reveal.js presentation instead of a PowerPoint or other. Um, what was the other mistake? Maybe that I forgot things. So the best way to engage with this tutorial is going to be good to go to my website. So if you go to the conference website, and then detailed program. I think there are other ways to get to the tutorials. Scroll down to parallel session 10, go to my tutorial, view the details, maybe, then click on the website. That was the other one. The other one was I made the mistake of assuming that I was done last week and I wasn't going to make any changes to my materials here. And that's just sort of impossible. As I was watching presentations throughout the week, I'm always sort of compelled to add things from other talks that I saw. My original day for this tutorial, I think, was Tuesday. So I thought, there's not much damage that can be done on Monday and Tuesday morning. So I don't need to make changes to my presentation. But then they moved me to Friday, and then I added a bunch of slides, rearranged things. And so I was very worried that I was going to ruin my website. So I didn't actually change any of this. Instead, like a good software engineer, I just added like a dev version of it. So if you go up to the top and then add dev to it, you'll get a version of the website that's like slightly more up to date, a couple of little extra links in it, but not much different. All right, a couple of other just bookkeeping things to start with. I would like everybody to open the Google Sheet in a new tab, like I did not do. I don't know how well this is going to work. When I'm teaching a class over Zoom, at my college, this is often what I'll use as a way to interact with people. It kind of assumes that you're willing to be interactive, but it is Friday. This is the last session where you might be, trying to learn something. So if you're just like brain dead and I don't get any interaction here, it may just not be worth it. On a Tuesday, it probably would have been worth it, maybe not on a Friday. So there are a couple of versions of me doing this tutorial. One is being very interactive and like making you think and interact with me. And another is where I like kind of put you to sleep by just like talking at you for the entire period. And you obviously won't get a lot out of that version of it. But I just thought I'd give you the option. It is Friday, last like real session of the conference. How interactive are you prepared to be? So just like give me a response up here, high, medium, or low. How interactive are you willing to be with me? I'm not going to judge you if I see a lot of low, by the way. Somebody may have come in after I described how to get to this sheet. If you go to the conference website, go to the tutorials, click on my website, and then from my website, scroll down and click on Google Sheet. You'll open up this. Okay, so there's no low. So I'm not going to just like drone on and talk at you the whole time, which is kind of nice, because that's not very fun. And let's see if my use of keyboard shortcuts work with a different keyboard. Yes. All right, the next question I have for you then is just what's your experience level? This is really aimed at beginners, beginners to the idea of like simulation. Maybe you've used a simulation engine before, but it's kind of like how when I'm teaching a neural networks class, a lot of times those students have used like PyTorch or TensorFlow, but they don't really know what's going on behind the scenes. So I'm asking like, how much do you know what's going behind the scenes with simulation? What's your experience level there? So high, medium, or low for simulation itself. You could be an advanced practitioner in terms of like, turning out publications, having a lot of good evolutionary robotics research that you're doing and still not necessarily know a lot about the simulation itself. So not necessarily. There's a lot of different types of simulation. And you've probably seen a ton of different types just here at the conference itself. I'm going to focus on rigid body dynamic simulation. But really, I just more broadly, like cellular automata, that's a simulation, but much different than what I'll talk about today. So, okay, it seems like a good crowd for the way that I've created the tutorial. I had no plans if you were all like advanced. I guess we would just like sit around and like come up with a new project together. All right, well, let's start my little presentation here. This is just on the website. So if you click on this, you'll have the same presentation up on your devices. It seems to work okay on phones and iPads. This was the risk that I thought, because if the internet wasn't stable and wasn't working, it would have just been a really boring PDF. This is really just for being able to click through it. I'm just going to skip through that. All right, so far, I just wanted to highlight a couple of the things I have seen, so we can talk about evolutionary robotics. What is evolutionary robotics? Well, there are different forms of it. Oh, okay, I just clicked on that. Here is one nice one. And so this is not the type of evolutionary robotics we'll talk about today, but it's definitely a form of evolutionary robotics. So you could call this soft robotics. This is a different type of simulation. It's essentially a bunch of little spring and damper systems that's being used to generate different behaviors. That's one form of evolutionary robotics. Luke is actually here. This is a very related form of evolutionary robotics, also built on spring and damping systems. And these are two tools that, if you were interested in getting into the area, that I would encourage you to look at. This is one, I think, Luke, you can correct me if I'm wrong. You said sort of next week, this is going to get some more polish, and the GitHub repository linked at the top here will make this pretty usable for other people that want to do similar type of experiments. This is sort of a tensegrity soft robotics style thing, also sort of built on spring and damping system. That's not an area of research that I've really done much work in. Anybody have any comments on the difference between this one and the previous one? I actually don't know. I'm supposed to be your expert up here, but I don't actually know. Luke, have you played around with the other form of soft robotics before? Yeah, thanks. I put you on the spot. Yeah, sorry for that too. Thank you, though. I started out, I think was it Monday? Was the evolution of things on Monday? Started out with a bang on evolution of robotics with evolution of things. The big difference between the stuff that you would find in that, was it a workshop technically? That workshop and the kind of work that I do is I'm less on the open-ended scale of things. And then for anybody who didn't see it, Michael Finn's project, basically making like the work from Carl Sims, I guess that was 30 years ago, more accessible. So I don't know exactly how he has this pitched, but next time I teach a computational intelligence class, this is definitely a tool that I'll dig into. On the, again, sort of more on the open-ended spectrum compared to the kind of things that I end up doing. All right, so now we'll get into sort of the meat of this tutorial. I'll just try to get us on the same page with respect to a little bit of terminology, although I have a feeling that'll go pretty quickly. And then we'll have this sort of loop where I'll present for a bit. I'll ask you to read along through an exercise that's on the tutorial website. And depending on if anybody wants me to, I might like sort of circulate. I'll lead a discussion where you can ask questions on our shared Google Sheet, and I'll answer questions, or other people in the audience can answer questions. And then at the end, we'll have some time for discussion at each part of the loop. And then at the end, the last demo essentially is going through an entire, from beginning to end, evolutionary robotics experiment where we build a simulation. I I'm not going to do this live just because it sounded like a nightmare to try to do live. I run the simulation, 10 replicates in parallel, and then we look at how to analyze the results from that simulation, a really small little toy example. Okay, a little bit about me. I'm a professor in the computer science department in Pomona College, and I have like sort of this obsessive compulsion to learn about simulation and different simulation engines. And so the way I've pitched this tutorial is I learned a lot about that, so you don't have to. And it might be me just like trying to make myself feel better about having spent all that time learning about different ways to do simulation. So yeah, this is my addiction essentially. I've have papers and research projects using Simulink and MATLAB and Julia and SymPy and just some finite element analysis. I've used, these are probably physics engines that some of you have heard of before. So using the Open Dynamics engine, ODE, Bullet, Dart, Box2D, Chrono, Project Chrono, it used to be Chrono Engine, Mujoko. I've used Gazebo and Weebots. Gazebo is actually built on top of, used to be a number of different engines, but now mostly Dart. And most recently, actually, most of my work is using Unreal Engine and putting aside some of the physical simulation and focusing on simulating vision. And Unreal Engine's really good for that. Anybody ever heard of Unreal Engine, actually? Whenever I ask a question, I'll try to just like flip back over to this in case people don't want to speak out loud. But feel free to speak out loud too. Anybody heard of Unreal Engine? A few people. So it's mainly made for video games, like really high fidelity graphic video games. And so we basically in my lab use it to generate computer vision data sets and do simulation in that realm. And then, yeah, I'm guilty of like building my own physics engines as well. And actually, I've seen a few other new ones this round at A-Life that I'll probably spend too much time looking at too. This is supposed to be a nice interactive visualization. Does this show up on any of your devices? Anybody actually following along? Does it show up for you? Okay. Let me just try to refresh the page and see if that does anything. It's not really a big deal if it doesn't work. Slightly disappointing. If I can do this quickly, I will. It's basically just an iframe anyway. And it could be that this computer just has iframes blocked. So if I just open in a new tab, that works. Okay. So this is the kind of thing that I do on a more regular basis. I don't do open-ended evolution for the most part in my evolutionary robotics work. Instead, I do really like directed optimization. So here's a little four-wheeled unmanned ground vehicle that's basically just supposed to chase this sphere around the environment. And I was optimizing things like the control parameters, the shape of the wheels, the track width, the wheelbase, and then also, I don't know how easy it is to see. This is a little visualizing tool that I built for this purpose, actually. If I zoom in, you can also see these little dots sort of on the peripheral of the wheel, like radially from the wheel. This one also evolved what are called transformable wheels. So this is an abstraction, and one thing that we'll talk about a little bit today is the whole thing is basically spheres as far as the eye can see, just because they're really cheap and efficient to simulate. But those spheres represent like little struts that go out from the end of the wheel. And I was also optimizing how far out do they go and how many of them are there. So that's a really good use of a gradient-free optimization algorithm like a genetic algorithm. If anybody's curious about this tool, I'm happy to talk about it later too. Essentially, I can just embed a link like the one at the top here on the bar, the URL bar, into a paper, and then somebody can click on it and open it instead of like a YouTube video playing or a Vimeo video playing. They actually get this nice visualization and they can drag around. It has a few other little nice things like getting rid of colors if the color choice from the original person was not colorblind friendly, for example. Okay, so that's the type of work I do. In my head, the kind of research questions that we ask in evolutionary robotics are, wide and varied, but I'll really just focus on two types of questions for like my demonstration today, my tutorial today. The first being, you're trying to optimize something for some sort of performance or novelty. So you can ask something like, how do I optimize the design of a robot for a specific task, like chasing that little sphere around an environment with blocks? How can we explore the possible space of designs and behaviors? So something like novelty search. That's one thing we like to do. Oh, and then we can also talk about open-ended evolution. On the other side, when you're doing evolutionary robotics research, something else that some of my colleagues do, this isn't really my focus, is look at algorithm design. So how can I craft an algorithm that best produces the result? Instead of trying to optimize the result, I'm trying to optimize the algorithm. Like, what can I tweak? What can I look at in the algorithm? I've seen a few papers on it at this conference, actually. One of my favorite multi-objective algorithms now to use is called Lexicase. I don't do research on Lexicase, trying to make Lexicase better, but I do use Lexicase. So that would be sort of the nuance I'm talking about, algorithm design versus like actually working on evolutionary robotics for like an application. Okay, this is probably something that you're all familiar with, but like I said, I'm just trying to get us onto the same page in terms of terminology. So when I talk about evolutionary robotics, this is sort of the loop that I have in my mind. You've got your population, you initialize it probably randomly, but maybe also with an initial seed, a seed individual. You evaluate it, and then you go into your main loop, where you, over some number of generations, or although you can stop early, and I'll talk a little bit about why you might want to stop early, you do your main evolutionary operations. So you select individuals, you modify them, you again evaluate them, and then you figure out which ones you want to carry over into the next iteration. And I'll be showing you a Python implementation in detail. And actually, there's a link to code for the full example on... I lost my website, didn't I? Oh, no. This is probably the easiest way to get back to is just open another tab. If you scroll down and click on the GitHub page here, you can look at the full code for everything I'm about to show you. I'm just going to give you like an abstracted view of all of it today. But yeah, you might want to define things like what is fitness, what's your genome, what's your individual, what is your population? And here's a simple way to define all those things. So for me, in the example I'm going to show you, fitness is really 2 values, and I'll tell you why it's 2 instead of just 1. I'm a big proponent of using both like a viability or feasibility value along with a fitness value. Here, I'm not doing anything more complex. My genome is just a list of values that I'm optimizing. And then my individual is just those 2 things paired together. And my population is just a bunch of individuals. Each one of these steps here, initialization, evaluation, stopping, select, modifying, combine, those are all areas of research. You can think of what's the best way to modify my selected population or what's the best way to evaluate them. I'm just going to take this really bare bones version of evolutionary computation and run with it for the examples today. Okay, so this will be the focus of today's talk, the simulation part of evolution and evolutionary robotics. And there are, in my estimation, these main types of simulation that you'd see for robotics. There's the analytical form, a numerical form, rigid body dynamics, which is really just numerical dynamics with some extras on top, usually just like some sort of collision solver on top. Soft body dynamics, finite element analysis, digital evolution, cellular automata, that kind of thing as well. And the bolded part there, the rigid body dynamics, is really what I'm going to focus on for this tutorial. All right, and the next few slides are really boring, and they're just like me giving you a bunch of advice without context. So instead of just jumping into those, what I'd like to do instead is have you, I'll go back to those. I basically had this presentation. I assumed on a Friday you'd all be tired and not want to be interactive, but you told me you were going to be interactive. So I restructured it for being tired, but instead I'm going to have you now jump to the first online demo here. So if you go to the second to last slide and click on analytical models, you can also click on it by just going to the website. And again, I'm going to ask you to go to like the dev version. I created because I didn't want to break the full version, the original version. And again, you can click on Demo 1 Analytical Models. And so that you don't have me just droning on for the entirety of the tutorial, I'm just going to give you a few minutes to read through that. And as you're reading through it, if you have questions, please just throw them up on the shared Google Sheet. And a few people just came in. The shared Google Sheet can just be reached on the main page of the tutorial website. Feel free to throw questions on there now if you have them for me, or if you have any questions before you start looking through that first little demo, let me know. Any questions to begin? All right, like I said, I'll give like a legitimate, let's say 3 minutes here to kind of skim through that article. Oh, I should also say, sorry to interrupt you if you're already reading it. One purpose of this website is I'm just going to keep adding to it as things come to mind as I get comments from you all. If I get pull requests that update the website and add new information, I would love that. So this is a resource that I'm hoping if you are an advanced evolutionary robotics expert, you can hand off to your new PhD students as they come in or undergraduate students as they come in. Or if you're a new student, you can look at this after this week, after you've had a chance to digest the conference. You can use it and use it as like a launching off point to getting started in evolutionary robotics. So it'll stay up. It's sort of impossible for me to know if I've given you too much time because since I wrote it, I just like breezed through it. Anybody want more time to read through that? I'm seeing a lot of like head shakes. No, that it was probably enough to at least get the general idea. There was one question in the meantime. If anybody's curious in that tool that I showed for visualization, I just put a link to it on the Google Slides, sorry, Google Sheet. Yep, just this visualization tool. Essentially, you can add it to any project. I have a little logger script that I have that'll output the correct data format for Python scripts and for C++ scripts, C++ programs. It's just a really simple JSON format. You can also just create your own in probably a half an hour if you know how to write like your own JSON schema. Anything else I should mention about it? It hasn't been touched in 2 years, but I kind of think of that as a good thing. It's not a dead project. I still use it all the time. It's not going to break on you. So there are some things I want to add to it that I just haven't had the right student focused on working on it. Yeah. Any other questions before I carry on? The main gist I want to have you take away from this first demo is for anybody who's had like a physics class, back before you were a college student, or maybe as like a physics class you had to take as an undergraduate student, you might have sort of this thing in the back of your head that, oh, it's just physics. I should be able to come up with a closed form solution for a lot of the things I'm trying to do. I want to know where this thing is at time 20 seconds, and then I just plug it into an equation, something like, like an object falling, where you have like an initial altitude, initial position above ground, the initial velocity, and the gravity, the acceleration. I should just be able to use, position is equal to initial position plus times initial velocity plus 1/2 AT squared, something like that. I should just be able to use that. That's only for really simple situations where you have nothing dynamic in your simulation. So dynamic actually just means from one time to the next time, you're not depending on where you were the previous time step. You're not relying on dynamics from the previous time step. So in this really simple case of our wheeled mobile robot going across the screen, I don't actually even need to simulate this. I can just say, where is it at time 20 seconds with a closed form solution? But it does mean I can't do things like interactively add a wall into it in the middle of the simulation. I'd have to recompute everything from scratch if I did that. It does mean that I can't do something like give this a controller that is dynamic, changes the behavior of the robot as it interacts with its environment. You can't do that with a closed form solution. So that's the limitation of this really simple, cheap, and easy to use simulation. I can sort of fake it. So I have a distance sensor here. It rolls across, and it looks like this is a dynamic simulation. But really, I'm just saying for all time greater than whatever the time it takes to get past this point, just don't let it move any further. It's just like fixed at that location. So I couldn't add another wall at time 5 seconds and have it react to that new wall. I'd have to resimulate the entire thing from scratch. So that's the limitation. I can't have anything dynamic. If I wanted a really simple proportional controller, like what I have here, I just can't implement that using a closed form solution. You can fake it, and you can say, okay, as I move through time, I can just recompute from the beginning as the wheeled mobile robot gets close enough to the wall. So I could say, okay, I know it takes 5 seconds to get into range of the distance sensor. Well, that first 5 seconds, I don't have to simulate. But at some point, you're going to have to do something iteratively. You're going to have to update it on the fly. And that would lead into the second demo. So the second demo is, well, what if I do want this to be dynamic in some sense? I want to add obstacles on the fly. I want the behavior of the system to change on the fly. You would use a numerical method for that. And really the big difference is the difference in these two equations, equations 1 and 2. So equation 1 is the closed form solution, and I can just tell you at any given time where is the robot based on that equation. Given the initial position, the angular rate of the wheels, the wheel radius, and then the time, I can tell you where it is. Equation 2 is the numerical solution, meaning it now depends on the previous time step. So you can think of it as like integrating through time. That's the big difference between those two equations. In the simplest case, at time step 1, if I'm going with like discrete time steps here, the two equations would be the same essentially. All right, other questions before I have you look through this numerical version? I'm not going to delete this link entirely. I'm just going to move it up here. That way, if somebody does want to look at it, they have a chance to later on. Questions about the closed form solution or like leading into the numerical version? All right, well, I'd like to give you a little bit more time to read through the next demo then. So the next demo being the numerical solution, the numerical version. And again, feel free to put questions on the sheet as they come up. All right, hopefully I've given you enough time. Any questions, anything you would put on the sheet or ask aloud? What questions do you have? I don't see any gray boxes that indicate people are typing. So I'm going to move away from this and just highlight a couple of the important parts from this version of the demo. So this is actually not too far away from what something like MATLAB, Simulink, Julia, like numerical tools will do. The big difference is this equation here is just a little bit more complicated. That's the actual integration step. If you want to learn more about integration, I think, this article I've linked down here, Fix Your Time Step. There's a pretty good series of articles that just talk about numerical integration there. I'm not going to spend too much time talking about it just because that's not the focus of somebody who's doing evolutionary robotics. I'm just trying to sort of show you what's going on behind the scenes. But yeah, this integration step is where things get more complicated. This actually perfectly follows the closed form solution with like a little bit of error between the two due to numerical differences. Floating point numbers aren't exact, and that's really the only error between the two. That's because this simulation was extremely simple. There's no force, actually. This is just a constant acceleration. Actually, it's a constant velocity system. The second we put this thing on an incline and have gravity, or have external forces applied, external forces and not just like external velocities, this, it's called Euler integration, will no longer work. It'll very quickly lead to errors. Then you can use something more complex, like an implicit integration or an explicit integration with multiple steps in between, where you're taking into account accelerations. But this is, like I said, this tracks perfectly with what we had before, because constant velocity over the surface. It even works in this dynamic case where I'm changing the velocity. This might seem, because I'm changing the velocity, might seem like it's not constant velocity, but it's always constant velocity. I'm just changing it using sort of stair steps. The velocity doesn't change over an integration time step. So that's what I mean by constant velocity. It does assume that my vehicle has like infinite acceleration and can go from like 1 meters per second to 1.1 meters per second in an instant, but it still works, tracks pretty well. Another thing to highlight from here, this was a mistake that I made in a lot of my early studies. Don't always assume that everything happens in the same time periods. So this actually includes 3 different time periods. My integration step, my control step, and then a render step. Those can all happen at different times, and I would definitely encourage you to have your control updates at a different rate than your physics updates. Physics updates should be pretty small. Whatever the largest value is that you can get away with your simulation being sort of accurate enough for whatever problem you're trying to abstract away from. For a wheeled mobile robot using something like Open Dynamics Engine, you probably want to use like at the highest 50 milliseconds, but probably like 1 millisecond or half a millisecond, something like that works pretty well. Unless you have really stiff springs involved. And an example I'll show you here, I'll actually add a suspension to the wheeled mobile robot. Then you need to reduce your time step. It's a bit of an art form. You just want to simulate, see what the behavior is, reduce it, maybe do sort of binary search type of process. If 0.1 seconds doesn't really give you a good behavior, then go down to 0.01 seconds. If that doesn't, 0.001. If that works, then maybe double, do sort of a binary search in that sense until you find some good bounds. But your controller time shouldn't update every physics time step. So for example, when I have a wheeled mobile robot, if I'm going to put this controller on a real device and actually have it like go up to a wall and try not to run into a real wall, if it's running on a microcontroller, like an Arduino microcontroller, I can probably only update the controller 100 times a second. So just decouple those two things is one of the first things I would say. That's probably different than anything you've heard before. My first sort of practical advice. Follow-up questions from anything that I just rambled on about there. Okay, so numerical solution, actually not that hard to implement. Even the to give you a fancy name for a pretty good quality general purpose integration solution, Runjacutta. I should have looked up pronunciation before I just said it in front of an audience. I think it's Runjacutta 4 is a pretty good explicit integration algorithm. That'll give you pretty good results if you put this thing on an incline and put external forces on it. Pretty stable too. I just threw some terminology out there. By stable, I mean the numerical stable is not going to end up with this thing like sort of flying off into space. How many of you have done some sort of evolutionary robotics experiment before with like rigid body dynamics, for example? Okay, for the hands up, keep them up if you never had it explode and like have the simulation. Yeah, okay, no hands are up anymore. Yeah. So that's a pretty common thing to have happen. You get some weird numerical instability. RK4 is pretty good at not having numerical instability. Just more computational workload though. Okay, so what if I wanted to add this step and have it like go over this green step? That's not supposed to be in the foreground. It just like, goes through it here because I'm not actually simulating it. What if I want my simulated robot to actually climb over the step? You can do that with everything that we just discussed. Not necessarily an Euler integrator, but RK4, for example, can handle this. What happens is when you detect that contact point, which is actually pretty easy to compute when you're dealing with circles and spheres. I mentioned that before. As much as possible, try to simulate your things with that have a uniform distance from the center of mass, because then it's just like a single distance check to see if two things are colliding. So what's the collision between two circles? You get the distance between their centers, and then you compare that distance with the combined radius, like radius of one versus the radius of the other. If the distance is less than the radius 1 plus radius 2, then they're colliding. Same thing with spheres, same things with hyperspheres and higher dimensional spaces. When you start colliding a circle with a square like this, it gets a little more complicated because you have to know what direction is the circle coming in from. So that gets more computationally costly. If you have two squares, it gets more costly. If you have two three-dimensional cubes, it's even more costly. That adds up to being twice as long to simulate, something like that. So not an order of magnitude necessarily, but if your simulations take a day, you're talking about 2 days versus 1 day. And is it worth that trade-off for the abstraction level that you're trying to find? So for some projects, probably. For others, probably not. So we could do that. I could detect the collision with the circle and the square, and then what would I do? I would actually add a little bit of a force going from the square against the circle, pushing it away, essentially. That is not so bad if my square is fixed and not moving around, and I always know exactly where it is. If I add multiple steps, it gets a little more complicated. If then I make the steps themselves dynamic so that it hits it and they both kind of roll around a little bit together, it gets even more complicated. If I add new shapes, new types of collisions between my objects, it gets even more complicated. And at some point, it's just not worth writing your own code for that kind of thing. And that's what the next demo talks about, is essentially what are called rigid body dynamics. It's everything we just talked about with numerical simulation. It's just adding all that complexity. Maybe I shouldn't say adding. It's hiding that complexity behind the scenes. So if you use something like Open Dynamics Engine or Dart or Chrono or Mujoko, it's doing all of that. And it has some really efficient algorithms for doing so. And it's more likely to be unit tested and not have problems. So calling this different from the previous is maybe a little disingenuous because they're both essentially numerical simulation. But I'm going to call it rigid body dynamics when you're not worrying about customizing anything. You're just going to use an off-the-shelf library. At this point, I think you all get enough of the gist of the demos that I'm not going to just like send you off to read the next 2 demos on your own. I just wanted to go slow to start with. That way we're sort of all on the same page and can interact with the demos individually first. So now I'm just going to go through those demos with you, and I'll try to add a little bit of narrative to it. If you have questions, I would love to get questions. If not, that's also okay. As I said, I'm a little bit addicted to simulations, simulation engines and physics engines. And so this is a rigid body dynamics engine called Planck.js. It's written in JavaScript because I wanted something I could embed into the web browser because I wanted an excuse to use another physics engine. I could have just created videos for all of these. But for anybody who's done 2D physics before, rigid body dynamics before. You've probably heard of Box 2D. It's been around for quite a while, like 20 years or so. And Plank.js is basically just a manual port from C++ to JavaScript of that physics engine. So later on, we'll actually use Box 2D and Python, and it's pretty much the same results here as the two algorithms, or the algorithms they use behind the scenes are pretty much the same. Okay, so here's the same animation that we saw before, but you'll notice a couple of differences. One is when it gets to the end, it kind of bops up a little bit because it actually has a real collision with the wall. I'm not just telling it, hey, there's a wall there, you can't move anymore. And then at the beginning, there's also a nice friction model between the ground and the wheels themselves. So you'll see it actually spin out a little bit, and it'll take a little bit of time to get up to full speed. So spin outs, get up to full speed. I'll play that again at the beginning. One last thing to look at is the chassis actually dips a little bit because I added a suspension to it. The chassis is the blue box. It's the main part of the wheeled mobile robot. So all of those are sort of given to us for free when we move away from doing our own custom numerical simulation to use something like a rigid body dynamics engine. We could do a fixed chassis. We could get rid of some of these and make it look more like what we had before. But it's kind of nice to have a little bit more, like, I guess, realism in this case. So yeah, there's gravity acting down. That's actually what's causing it to propel forward. Without the gravity, it would just sort of hover off the ground and float away. If I thought about it, I would add a little checkbox here to turn off and on gravity. Because this actually is simulating behind the scenes. It's not just playing back an animation. It's a full simulation. Any questions about this setup here? What's different from this to what I was showing before? And again, you can ask on the sheet, you can ask out loud, either way, either version's fine. You'll see pretty much the same format for any rigid body dynamics engine that you use. They all start with essentially creating the world. And here I'm creating the world with gravity of negative 9.8 meters per second. Be careful to look at the actual documentation for units. For the most part, you can think of a physics engine as entirely unitless, and as long as you're consistent in what you're giving it, it'll work just fine. Some do make some assumptions about your units. So for example, Box 2D and therefore Plank.js actually do assume you're using kilograms for the masses, meters for any sort of distance units, radians for angular velocities or for angles. But yeah, they'll start with a world, and then you just create your environment. So in this case, I'm saying I usually start with my static things, so things that don't need to react to physics. You'll almost always have some utilities for, things that are easier to simulate. So if it's static, it doesn't react to gravity, and so it's cheap and easy to work with. You don't need to worry about its mass, essentially. Instead, things just collide with it. So for Plank.js, we create a body, we call it static, we give it a position, and then Plank.js calls it a fixture. Box2D also calls it a fixture. We have two different parts of every rigid body. There's the dynamic object and then the collision object. The dynamic object, I think I have a table below. They're mostly just called bodies, but some physics engines will have a different name for them. So if you look at the body column, some call them bodies, some call them skeletons, some call them links. It's the part that reacts to accelerations or forces. And it can be a point mass. It doesn't actually have to have any shape to it. You apply a force to it at a specific point in space. It doesn't actually have to be acting on the center of mass. If you don't act on the center of mass and you're off the axis, then it'll give it a rotation as well. But yeah, that's the body part. Doesn't collide with anything. It can just move around in space. And it's when you add a shape to it, when you attach a shape to it, that it actually collides with other things. So I've done a lot of aquatic simulation. I should have put some videos on here of some of the aquatic simulation I used to do. A lot of robotic fish, actually. And we just didn't have any collisions. And it made our simulation, probably 100 times faster without collisions. because that's where you spend a lot of your computation. So I got away with no collisions in my aquatic simulation because it was basically a robot just floating around the planar surface of the environment, not colliding with anything. We were just looking at how do you best apply forces to the tail fin to get it to propel forward. No collisions needed for that. But for the most part, the reason you're using a rigid body dynamics library is so that you can actually have collisions and have them objects interact with one another. So for this environment, I have ground and I have that wall that sits out at the end. And then I have some dynamic objects as well. So I've got the chassis and then the two wheels. And those are created from bodies. I'm having trouble scrolling, sorry. And then you attach a shape to it, so a box shape. And then you can also specify on the fixture things like the density and the friction. So yeah, usually two different components for pretty much any physics engine you'll use. And if you're wondering why it has two different pieces, for the reason I just said, it's not always useful to have something that collides. Sometimes you just want to be able to move something around without it colliding. In 2 dimensions, I'm clearly using a circle for the wheels. For the most part, what do you think I use in 3 dimensions for the wheels? If you've been paying attention. Yeah, I go to the 3-dimensional equivalent of a circle, which is a sphere, which often looks kind of weird. But if I go back to this example and show you some of the things I've worked on before. Here's an autonomous, oh, that's a new error. I don't know. Do all these have that same break? I just said it was stable and then something's broken. Oh no, it did work. I don't know, just some live demo voodoo, I guess. So if I zoom in on this, it looks like those might not be spheres. I'm actually just not rendering them as spheres, but they are spheres. This is a smooshed sphere. It might look like a cylinder, which is what most people would use for for simulating a wheel. Cylinders are a pretty bad thing to use for a wheel. If you think about something with a little bit of width, it has a very flat bottom, and no wheel in existence is going to be perfectly flat on the bottom. And then when it collides with things, it gets very it vibrates a lot. Essentially, it'll sort of teeter back and forth. So you'll actually get better results, something that transfers better to reality with a sphere than you will like a cylinder, for example. So I'm using cylinders. Okay. And then after you have your bodies and your shapes, ODE, for example, we'll call them geometries instead of shapes, you connect them together. So I'm going to connect the chassis and the front wheel with a wheel joint. Box2D and Plank.js are really nice. They actually have a built-in wheel joint, which means it'll give you a nice API for generating torques, like motor torques. And it'll also have this built-in suspension to it, both of which you can just get rid of by if I set suspension frequency to -1, for example, there's no suspension there. It's just a rigid connection. Other dynamics engines will have slightly different concepts here. Like it may not have a wheel joint. Instead, you might have to use a revolute joint, and then you have to manually implement a motor on top of it. So I'm just kind of cheating here and just using a physics engine that I know works pretty well for this type of thing. And I can just set the motor speeds. And my simulation algorithm here, like the high level here, looks pretty much the same as what I had before. This is the only line that's different. And instead of me doing the numerical integration, I'm just saying, hey, world, take a step. And it does the numerical integration using a much better algorithm than I would want to try to implement by hand. So during that, it moves everything forward. It applies all the forces, moves everything around. If two things collide, it'll actually do clever things like if they penetrated, it'll move them back out apart and have it recoil essentially. There are other clever things you can do if you want to turn them on. They take a lot longer. If you have an object that's moving really fast where it would appear at one time step in front of a wall and then another time step on the other side of the wall, you can actually track that through and prevent things like that from happening. The reason to use a rigid body dynamics engine is so you don't have to implement any of that for yourself. So now our last nice demo here before we move to like a full evolutionary robotics workflow is to show that this does work with a step. So I'm going to now evolve this little wheeled mobile robot to do the exact same thing. So I want it to go forward, hop over a step, and then once it's over the step, stop in front of the wall at a specific location that I'm not actually going to tell it. If it runs into the wall, I'm going to penalize it. If it gets stuck on an object, I'm going to penalize it. I'm going to reward it for things like doing this quickly and doing it without like tipping over. But before I jump into that, I do want to give you all a chance to just think about and just throw ideas out here for like what the objectives would be. So what would you put as part of like your fitness function, essentially, if you were trying to do what I just said, which is get this robot to get over the step and stop in front of the wall? How would you evaluate that? And I just added anywhere on the sheet, essentially. Get closest to the wall without collision. Exactly. And so what would your metric be? It's like, how would you evaluate how well an evolved individual did? I'm not asking this in a very clear way. I'm sorry for that. It's also Friday for me. So, but yeah, that's exactly what I'm trying to ask is how would you get it to do that? What fitness function would you write so that your evolved individuals do that? Yes. Yeah, exactly. Distance from target to goal position. That's actually, I'm really glad somebody put it exactly that way, to goal position, because think about what your goal position sensor might be. You could actually do that. Like you could put like a little RFID tag on the ground, and then as the robot like gets over the RFID tag, it sort of knows the strength and it stops at the exact correct spot. I'm going to say the only sensor you have though is a distance sensor to the wall. So that's slightly different. So distance from target to goal position, that's definitely the objective. Duration till reaching the goal position, exactly. So one thing you might have happen if you just had that first distance to the goal position, if that was your only objective, you might have something that kind of creeps along pretty slowly and then gets there. But we're not encouraging it to do it quickly. And I think I even put on my like, this is what we're trying to do, quickly get to the goal position. If you don't encourage it, it's not going to happen. So we definitely want time as part of the objective function. Penalize a collision with the wall, definitely. Otherwise, you probably just have something that goes full speed, rams into the wall, and then kind of backs off a little bit, because that's probably the fastest way to do this. Definitely, you want that sort of collision, or sorry, that sort of objective, added to your objective. All right, then what would you evolve? There's no right or wrong answers to any of these, by the way. What are your free parameters? What are the things that you are going to optimize with your evolutionary algorithm? Just sort of throw some things out there as well. Yeah, those first two comments there, rotational speed as a function of distance to wall and motor speed. Definitely, we want to be able to control the speed. And you can't just control the speed. You definitely want to control it, but you can't just control it. You do want to do the second part there, which is control the speed as it relates to the distance from the wall. Exactly. Think if you were in the tutorial, what was Kai and Kara, what was your tutorial? Evolving bodies and brains, right? So think that too. Wheel diameter, that's exactly what I was sort of expecting to go up there too. Except for I call it wheel radius. I don't know why. I always like to evolve the radius. I never evolve the diameter. But. I also have evolving the track width. No, yeah, track width. No, wheelbase. Sorry, I always get those two confused as well. The distance from the front wheels to the rear wheels. I also have it evolving that, the wheelbase. So yeah, those are all things that we can evolve. And I tried to pick a contrived example so that I could demonstrate specific things, obviously. And that's the next step here. So in the final demo, I'll just show you from the very beginning, how do I go through this entire process? So here are the steps, and I tried not to leave anything out. I came up with this example, and I did it from the very beginning to the very end. I'll admit that I probably, if given an infinite amount of time, would have made it a little bit nicer, used a better logging system, for example. But I tried to keep the code really simple as well. So we'll look at how do you set up your computing environment, how do you create your simulation, and the important part here is that your simulation is decoupled from both evolution and from visualization. So you don't want all those things to be like hard to pull apart from each other. You don't want to have to visualize while evolving, and you don't want to have to evolve while simulating or evolve while visualizing. You want to just like keep all those pieces apart. How do you design a fitness function? Actually, I should probably rename that part. How do you not design a fitness function? Because I basically did exactly what we just talked about here is I thought about these different objectives and added them up. That's actually a really bad way to do this. And I have a pointer to a better way to do it. Something like NSGA2 if you're trying to do like multiple objectives, like not run into the wall and also get as close as possible. Or Lexicase is another really good way to do many objectives. But for this one, I did the bad thing. I just added these all up. How do you implement an evolutionary algorithm? It's arguable whether I should even try to put that in this tutorial. It's the world's worst evolutionary algorithm. It's just tournament selection, single point mutation, nothing, no bobs or fills. It doesn't work very well. It gets to a really good solution, but that's because my problem's really easy. And because I seed it with a good example. Actually, if I do a 10 replicates and I don't seed it with a working example, something that actually gets over the step, it actually hits a lot of local minima. And not all the replicates even come up with something that solves the problem, meaning it stops on the end point. That's because my algorithm's really bad, though. So I cheated and I seeded it with like a handmade example, essentially. How to launch the evolutionary process with parallelism, and then how to look at the results. I'm going to go through this pretty quickly because I think the real value of this last demo is that you can read through this at your leisure and then also go to the GitHub page and look at the full code listing for the entire project. I just pulled out snippets that I think are useful. These are all very opinionated, by the way, so like you're not going to offend me if you don't go with my route. I happen to use a high-performance computing system that uses LMOD and Slurm. Those might be terms you've never heard of before. It's also okay to do all this all on your laptop, and I have advice for like how to set things up if you're just doing it on your laptop as well. I like MiniForge, which is like a version of Anaconda that's not attached to like the Anaconda private company. And so I use MiniForge. I'll create Anaconda environments, install my stuff in the Anaconda environment. And then for reproducibility and just to be a good scientist so that I can share my results, I always export my dependencies, like the exact versions of dependencies so that I can share with a collaborator or somebody who reads my research paper and wants to replicate the exact results. Very important to share exact dependencies. And I usually do that in two ways. One of them is not very portable. So the first version there, the conda-end export from history is the very portable version. It means that I can give you this file and it'll install software on your computer and it should work pretty well. But you're not guaranteed to get the exact same results just because of slight changes between our computing systems, even hardware differences. The second one here, the explicit one, will give you sort of exact reproducible results, but it also requires you to be using the exact same hardware, exact same like operating system. Probably a better way to do that would be to use something like Docker. That's not a tool that I use very often though, but you'd be well within your reason to use Docker instead for the same purpose. Okay, so here's me showing you how I usually decouple simulation. I usually just create an independent class in whatever language I'm using, TypeScript or Python or C or C++, that just takes in the parameters and has nothing to do with evolution. It's just what are the things that are configurable on here. I probably should have put even additional parameters in here that I wasn't evolving just to show you that you can sort of have the two things being separate. And then I always add like a little flag at the end that says whether or not this time around I'm going to visualize something or not. Just build that into the simulation itself. So inside this class, WMR, Wheeled Mobile Robot, you'll see all that stuff I just talked about with Box2D or Plank.js. I'm creating the environment. I'm creating the bodies and the shapes. I'm attaching links to connect those things together. That's all shown in there. If you want to do an even better job of this, you would decouple the environment aspects from the robot aspects, but I just have them all in a single class since this was a simple enough example. And then how do you actually create one of these? So I can just create a new WMR by passing in all the different values. And that's pretty much how I would do that if I were visualizing it or just doing like a little demo and not evolving it. If I'm evolving it, it looks more like this. I've got all my parameters that I'm evolving. And then I'm going to scale them into the proper ranges. And then I call simulate and just unpack. So this is a Python syntax for unpacking a dictionary into the arguments for a class or a function. So pretty simple. I happen to like using this sort of API. This is a nice way to decouple even an extra step here, which is what are the ranges of my parameters and what are the ranges that are actually evolved. So when I write an evolutionary algorithm from scratch, I almost always just evolve values from 0 to 1 and then map them into the appropriate range later on. Slightly helps with plotting those genomes after the fact. If I always do it in one place, I know that the evolutionary algorithm is always using values from 0 to 1 for all the different genes. And then I know that my simulation is always using the scaled parameters. That one I could take or leave as a piece of advice. I happen to like it just because it makes it easier to plot things after the fact. It also means I can save this mapping into a separate file and then load it in multiple places. So I usually load it into the simulation or the evolutionary process, and then I'll load it also into my visualization script if I'm generating plots. Because I want to take the genomes from 0 to 1 to, for example, 0.3 to 0.9. Oh, and I should say, these are the values that I ended up evolving. The wheel radius, the length of the chassis, the suspension characteristics on our robot, the sensor limit. So anything beyond this value is just basically considered infinity away. So that gets taken into account. And then here are my control parameters. It's essentially a linear controller where you get to say where's the y-intercept and what's the actual slope of the line. All right, I mentioned this near the beginning of the tutorial, and I am coming back to it now. I said that I pretty much always, for evolutionary robotics, have two values as part of my fitness. One of those is a constraint or a feasibility or a viability value, and then the other is the actual objective value. And I tried to basically wedge that idea into this contrived example. And so this is why I evolved both the chassis length and the radius of the wheels. So if the wheel radius is really big and the chassis is really small, the two wheels overlap. And one way to handle this is just by saying, okay, that's infeasible. You just give it a fitness of 0 or negative infinity or infinity, depending on if you're optimizing or minimizing. I happen to like using a value for this, which just tells you how infeasible is your robot. And that gives you sort of a better gradient in quotes for your evolutionary algorithm to follow. So this is a constraint. And the closer, the more your wheels overlap, the worse that individual is. So it just doesn't get selected for reproduction. And then here's that really horrible fitness function that we sort of designed together. And I found that if I gave a really big weight to the distance, so 2 is the weight for the distance, that does better than if I sort of treat all these things equally. So this happened to be, the distance to the target happened to be the most important part. I also optimized the final velocity. What I didn't want it to happen is basically just continually roll, and then at 20 seconds exactly, it just happened to be over the target. I wanted it to come to a stop and be at 0 velocity over the target. So this is the final velocity, whether or not it hit the wall. I also minimized the wheel radius just to see what it did, because a smaller wheel gives you a better fitness, and it also makes you slower, and it also means you can't get over the step. So I just added that in as a way to see what the final wheel value came out to, essentially. And then how long did it take to come to a rest is the final little part here. So how quickly did it get to the end? And this fitness function actually does not work very well, like I mentioned before, unless I give it a working example. It hits a lot of local optimum. So the highest fitness values were almost always ones that got high centered on the step to begin with, because that was better than getting over the step and then running into the wall. So this fitness function sort of encourages getting stuck on the step. But like I said, I seeded this with a working version, which got over the step and just doesn't do a very good job of doing it like fast. This is what it looks like in code. There's nothing sort of eye-opening here. The only thing that I'll point out is that it's tempting if you're just in a rush to just return the final value, which is the final fitness value, and then discard all these intermediate results. I always keep those intermediate results just so I can save them and plot them over time, so I can see which objectives sort of were easy to start, were easy to solve at the beginning, and which ones were harder to solve at the beginning, and which ones were hard to solve even by the time evolution ended. This is being able to plot these values is how I figured out exactly like the characteristics of it getting stuck, being high-centered. For anybody who's implemented an evolutionary algorithm before, there's nothing particularly nice or jaw-dropping about my implementation here. The only reason I even put this on the page again is just so that we're all on the same page on like the actual dynamics of this one. And so if you were to run this, I always like to have like nice little visuals so I can see progress. This is me just running like a demo version of it with a certain number of generations, certain number of evaluations. And another thing that I'll mention is I actually ripped it out of this one, but you should always checkpoint your results so that if something crashes, you can restart it from where it left off. Let's say it gets 100 generations into a 1,000 generation experiment. You should be able to pick up at that 100th generation by all the data you're saving at the end of every iteration, something like that. All right, maybe more useful are these kind of details. This is a simple way, if you're using a system like I am, to launch multiple replicate experiments. So let's say that I chose the population of 100 generations for each population, and 10 trials, 10 replicates, 10 repeated experiments just seeded with different random values. This is one way that I could launch that task. I'm using something called Slurm, which will manage this all behind the scenes and make sure I'm not like abusing my hardware. But another good tool to use, which is linked if I like were to jump over to tools here, or advice actually, is called Parallel. GNU Parallel is a nice tool for running a bunch of these things and not stepping on your own toes in terms of what hardware you actually have on your system. I have some advice for if I were to go to this advice page or go back up to the presentation, some advice on how many processors you should use on your system. But those are all details that are probably better to look at after the fact instead of me just like spouting them out to you. So for saving the data, this is probably also not news, but pandas data frames or polars data frames are a good way to do that. And save as much data as you can is sort of the theme of it. You'll almost never save too much data or run out of space with just text files. So I'm saving like fitness values and feasibility values for every generation. I should also be, but decided to keep the code simple. I should also just save every single individual from every single generation, just because it's, like I said, it's megabytes of space that's worth keeping around. And as simple as just to put them into a data frame and call like 2CVS, or you could pickle them if you'd rather not serialize to CVS, or sorry, CSV. If you'd rather not serialize back and forth from comma separated values, you could all just also just save the data frame directly. And then after the fact, you'll have multiple sets of data, so one for each replicate trial. I like to aggregate those all into what's called a tidy format or a long format data frame. And this is my code for doing that. And I do it so infrequently. I rewrite this code so infrequently that I always forget to do it. And that's why it made the website. Is nice little snippet that I can copy and paste in there and grab each time. So I'm going to grab all the generation comma separated value files, read each of them into a CSV, and then you call concat at the end. And now you have a nice data frame with all of your data across all replicates, all ready for plotting. For visualizing, I always start by looking at the behaviors themselves. Did this run on anybody's laptop? I don't know why it didn't here. Maybe if I do a refresh. Okay, both loaded this time. I don't think that's a problem with my visualizer. I think it's probably a problem with the network. So here are a couple of versions. Let's see if I can use this keyboard enough to. There we go. So here's one optimized behavior. Oh, and you can even see I use full spheres as a reminder to myself to tell you that I use spherical wheels instead of cylinders, for example. One optimized behavior, nothing overly groundbreaking in the results here. I think one of these teeters back and forth a little bit. Yeah, that one almost touches the wall, then hovers backwards. You can see that you do get slightly different behaviors here. It's worth tracking the behaviors actually. So if anybody's looked into like behavioral repertoires, it'd be nice to plot sort of exactly what kind of different behaviors we had. And then a bunch of plots that you've probably seen in 100 presentations if you've been to A-Life a couple of times. Plotting the generations. Really easy with a library like Seaborn. It's actually just this one line of code will give you a nice plot like we had above. The other lines here are just a little bit of styling, making sure I add a legend, and then saving the figure. I pretty much always recommend saving your figures as a vector format, just so you don't have to worry about scaling issues if you try to put them in your presentations and then also put them in your papers. This is actually not a Seaborn plot because I wanted to have like nice little interaction for the website here. So this is using a different one called Plotly. So there's code for this website that shows you how to generate these same plots using Plotly and then also Seaborn. And then final fitness values, also worth looking at. This also gives you an idea for the behaviors. So the final distance, it was pretty clear that that was an easy thing to optimize. Same thing with final speed. We were doing a maximization on the fitness function, but that's why that fitness function has a lot of like 1- parts in, because I wanted to minimize the final distance and so on. I told you I was minimizing the wheel radius, but you can see that it couldn't quite get down to the very bottom there, probably because any wheel radii like less than a certain value just can't get over the step, for example. And then the evolved parameters. One piece of advice that I'm always given by like statisticians is try to avoid box plots as much as you can. It's actually not statisticians that give that advice. It's statisticians that do like user studies on using statistical plots. Box plots are just not very good for humans. We have a tendency to interpret them incorrectly. So like a little short tail, people think, oh, there's not much there. It's not very significant. But a short tail on a box plot actually means there's a high density there. And these strip plots are a better way to sort of show you the density versus like a violin plot or a box plot, or you pick the distribution style plots. Our brains are really nice at picking out clusters of points. So we can pretty clearly see that a variety of chassis links work, but right around here is where you see like the biggest cluster, for example. Other nice things to see from this kind of plot that are a little bit harder to see from a box plot is I probably want to change my evolution range of different parameters. You can see for suspension frequency, I've got a pretty good cluster here that's all the way at the top. That probably indicates I wanted to say like, well, maybe what happens if I increase that range? Is there like a better range? Some of the ranges are due to physical limitations, so you can't always do that. But this type of plot does a good job of showing you your ranges. And then the final thing I have here that doesn't often get done is just showing correlations among parameters. So you can see, for example, the control parameters are pretty highly correlated, which isn't a huge surprise. The speed slope, so how quickly do you accelerate or decelerate, is pretty heavily correlated with the actual maximum speed that you are allowed to evolve to. All right, I believe that's the end of my time anyway, and we just got to the end here. I'm kind of surprised the timing was reasonable, but did any questions come up in the meantime? I don't think so. Any questions from any of you now? Yes. Hi. Yeah, I didn't explicitly. So the question was, how does he evolve to basically hit the correct location on the ground, the target location? And it just learned the control parameters that made it such that it stopped when it got to that based on the distance to the wall. It basically learns the relationship between distance to the wall. I shouldn't say learns. It evolves the relationship between distance to the wall and target location. Yeah. Mm-hmm. Yep. Yeah, I probably should have plotted it that control, the controller that's being used here looks kind of, I don't actually know, is it on this page? I think it didn't make the cut for this page. Let me go back to this one. It looks kind of complicated. Oh, all the way back here. The angular velocity equals the max of negative max speed min. It's basically just a clamping function. So it's like 0, ramps up, and over. And it just basically evolves the characteristics. So like how steep is the slope? And then, yeah, shifts it left and right, the whole thing. Yeah. Mhm. Uh, they cannot. So that's what the constraint does for us. So if the evolved parameters have the wheels overlapping, we actually just see how much do they overlap, and it never actually gets simulated. Yeah. So the objective ends up being 0, and the constraint value has some positive number. It's a good question. For the way that I use constraints, it's actually to give evolution more flexibility. So maybe my terminology wasn't the best, but I use constraints so that I can have really high ranges for my evolved parameters. Because another way to do the exact same thing is just to say, okay, well, the maximum value, or sorry, the minimum value of the wheelbase has to be such that the maximum value of the wheel radius means that they don't overlap. But I was basically like, I would rather have larger ranges, have really large wheels and really large chassis, and really short chassis and really small wheels. And so I just made those ranges really large. And if they're not physically realizable, then they don't get simulated because we can't simulate them. And they get a constraint value. And if they're really bad, the wheels overlap by a lot, meaning you couldn't construct it. It gets a really bad mark on feasibility. And then that gives you a gradient for like basically pulling those two wheels apart, either by making them smaller or making the chassis wider. It basically gives you a gradient from something that's not feasible to something that's feasible, as opposed to just like throwing it out and not evaluating it and giving it like a 0 objective score. Mhm. Yeah, I guess what I'm saying is that I like to be gentle with my evolutionary algorithm so that it can see the difference between two wheels that overlap by a lot and two wheels that barely overlap. Because if I initialize my population randomly, and let's say 80% of them are infeasible, I would still rather select the ones that are only a little bit infeasible than the ones that are really infeasible. Because then my my next iteration of individuals is more likely to have some where the wheels don't overlap. It takes like a generation usually to just get rid of. Like if I looked at the final population, almost none of them are infeasible, yeah. Except for the ones that like mutation makes them feasible and they get evaluated anyway. Yeah. As long as you have some way to measure how infeasible it is, I would still use this sort of method. Because it's better to know if something's just barely not working, it's good to know that so that you can still use whatever is in that genome potentially. Yeah, please do. Yeah, that's the picture I have in my head is essentially a flat, yeah. Oh, by the way, sorry to interrupt you. Feel free to run out. By the way, I think our time's officially over. Yeah.